Good evening, everyone. The topic for my presentation is simulation strategies for HBM design. Here's an outline of my talk today. I'll give a very brief overview of high bandwidth memory and high performance computing. I'll also introduce Nvidia's HPC platform and our H100 product which got released recently. Then I'll talk a little bit about the HBM design ecosystem and the signal and power integrity challenges in advancing the data rates. Then I'll talk a bit more about mixed mode simulation and our simulation strategies for the HBM memory interface. So the picture that you're seeing on the bottom is the H100 GPU. It has 6 HBM sites, as you can see. And then on the top is a cross section. It shows the HBM interface that's being routed on the interposer, and the link is between the PHY interface on the GPU to the HBM DRAM. You have a base die, and you also have the DRAM stacks in the HBM. The picture on the right it shows the data bandwidth trends over the last 14 years, and it also shows where HBM stands in terms of memory bandwidth compared to the other memory interfaces. And the key thing here is that we need to know what is driving all these data rates and memory bandwidth. So as you have AI applications and cloud computing, and all these require high performance compute products, and Nvidia is designing products to meet that need. And in all these applications, in all these areas, as the data sets grow, as the complexity grows in these data sets, you need more compute power, you need more memory capacity, and you need more memory bandwidth. For most cloud and AI applications where you do some sort of training, HBM is the memory of choice. If it comes to inference, you could use a mix of GDDR or LPDDR products, and you could have a similar mix for edge computing. So this is our Nvidia H100 Tensor Core GPU. It can support 80 gigabyte of HBM3, and the memory bandwidth is about 3.35 terabytes per second. It also supports HBM2E with a memory bandwidth of 2 terabytes per second. So if you look at the plot on the right, you can see that starting from P100 in 2016 with HBM2, the data rates and the memory bandwidth has constantly increased over several generations, and H100 we are able to target more than 3 terabytes per second. So trying to go from one generation to the other, like from A100 to H100, where you double the memory bandwidth while keeping a constraint on the cost and the form factor, is extremely challenging in terms of SI and PI. So we'll discuss a little bit more about the HBM design ecosystem and what drives some of the key factors there. Since it's a interposer-based interface, it is mostly point-to-point with straight routes with very minimal fan-out, and the die span kind of dictates the number of routes you can, routing area that you have on a single layer. Now, if you throw in more layers, then you can increase the pitch. So the die span and the number of route layers directly control the interposer pitch. Now, the number of route layers that you can have depends on the interposer packaging technology. And now, when you look at link performance, the usual suspects, insertion loss, crosstalk, and the channel length, which kind of impacts both insertion loss and crosstalk come into picture. Now, this doesn't give you the complete picture. You still have TX and RX features and the training that goes to make the whole link work. So all these are key components of the system. So next I'll give you an example of how all these components impact the actual performance. If you look top to bottom, you can see the impact of crosstalk. And if you see between the yellow and green, you can see the improvement in eye performance from one generation to the other. Apart from crosstalk and ISI, the interposer stackup also plays a key role. So I'm showing some key features of RLC between one generation to the other. So all these components kind of help us in improving the speed from one generation to the other, as shown here on the bottom plot. So next, let's look at some of the simulation-related issues that you would run into for a memory link. So usually you have tight design cycles, and you don't have enough time to manufacture a test chip, test it, and then go into a product. So verification through simulation is very important. Now I'll walk through an example, but the solution space could be pretty large. It depends on it could be applicable to any kind of memory interface, or it could be any interface. So the solution space could be large. And then you would have varying levels of model complexity. And as an SI engineer, you want the flexibility to incorporate different models from, say, different vendors. And you want to have the flexibility to incorporate models with different levels of complexity at different phases of the project. So I think all these are key things that govern your simulation and that govern how fast or how slow your simulation progresses. Let me walk through some of the strategies that we use. So to handle a very big solution space, to begin with, we are doing a solution space exploration. So we want a fast turnaround in simulation. We are okay to have reasonable accuracy. And at this stage, when we do the modeling, we are okay to do like a 2D channel model using 2D electromagnetic tools. And then we can have a simplified model for the transmitter and receiver. And at this stage, we just use PrimeSim HSpice to do all our simulations. So once we are able to narrow down on the solution space to get to reduce the solution space to something reasonable, now we can throw in or work with circuit models where we want to understand how the channel models work with the actual circuit and how that interaction is, right? So at this stage, we are okay with longer run times, but we want high accuracy. And this is also the time when we exchange models with the circuit team. So the circuit team would use PrimeSim SPICE and use our models to do the simulation, and we would still use PrimeSim HSpice to do the simulations. So by the end of this design phase, you are ready to finalize the interposer routing, and once you have the layout completed for this, you are ready to do a post layout. So you can use 3D EM tools to extract the channel, and then you would still use the same circuit and circuit models to do the simulation. And again, the same thing, the circuit teams would use PrimeSim SPICE, and we would use PrimeSim HSpice to do the simulations. So let me walk you through an example where in HBM design ecosystem, you could have like a huge solution space. So as I explained before, if you have just one layer and your pitch is 4 microns and your minimum spacing is 1 micron, you could have a signal width of 1 micron, but you could sweep your ground width from 1 micron to 2 microns. So in a similar way, you would end up with, say, 21 cases. And then if you sweep for drive strength, then you would have 21 times 4 as shown here. Now this is for just one stackup. If you are considering different topologies, or if you are considering different stackups, the number of simulations grows. Now if you were to repeat the same process for a two-layer stackup, then your pitch is now 8 microns, your minimum spacing is still 1, but now you have a wider range to sweep, so you end up with, say, 210 times 4 simulation cases, and so on. So you can end up with a huge number of models pretty quickly if you want to optimize the whole solution. So here is an example which shows the results for the solution space where the signal trace width was swept from a small value to a higher value on the x-axis growing to the right side. And then for the ground trace, in a similar way, the ground trace width was swept from small value to big value. And in this case, the pitch was kept the constant because that is a routing constraint. So the simulations were done with multiple crosstalk aggressors, and the impact on the victim for both crosstalk and ISI was captured, and the eye aperture is plotted in the contour plot. So as you can see, the solution space could be wide, but now we are left with a small contour of a dark red, which is our optimal solution. And within this, you could now pick, say, a handful of models which have different signal widths and ground widths, and you can do further optimization on these channel models. For example, you might see a difference between a signal trace width that is wider, and this might have a higher capacitance than the one which has a smaller trace width. So all these factors could be considered when you take this to the next stage where you do the simulations with the circuit model. So the eye diagrams on the left compare the simulations done with a linear TX and RX and simulations done with a circuit TX and RX. The simulation time, the number of nanoseconds of simulation time has been kept constant. So you can see the difference in the runtime. So it's several orders of magnitude higher. And like Randy mentioned, when you are doing DDR simulations, you need to take care of pull-up, pull-down mismatch. And if you look closely at the two eyes, and if you look at the blue bar, you can see that the blue bar is perfectly aligned at the eye crossing for the linear driver, but there is a slight mismatch for the simulations with the circuit driver. So we do want to capture these things, and the difference is actually about 1% of the UI at the speeds that we were running. Even though you're able to run circuit simulations, interfaces like HBM require very low BER. In order to generate an eye diagram with in order to generate a low BER eye diagram, you need to use simulation tools, as you can see, because the HSPICE runtimes are not acceptable when you actually use circuit models. So here is a snapshot of the statistical simulation process. So you use a pulse response to generate the eye. I think the previous speaker also went through this. Now, we spoke about different simulation environments. So the statistical simulation also gives you a different perspective on the link. So if you look at the pulse response, you can look at the cursors as shown here. So the H0 is the main cursor. So H0 is your main cursor, then you have your H1 and H2. So by looking at H1 and H2, you can see whether your link requires any equalization or not. And you can evaluate the same cursors at different drive strengths, like I'm showing here at 16 ohms, 18 ohms, and 20 ohms. And you can make equalization decisions based on like a statistical simulation. So the plot I'm showing on the right, it shows the BR, it doesn't show the BRI, but it shows the BRI metrics. So I have a BR15 eye height and a BR15 jitter measured at VREF. And if I use a 16 ohm driver and whether I enable or disable DFE, for blue plots, I have a DFE of 0, which is not enabled, and I enable DFE, it is in red. So as you can see, for a strong driver, I don't see any benefit in eye height due to DFE. But if I use a 20 ohm driver, I do see a benefit in DFE, and I'm also able to reduce my jitter. So it is possible to use behavior models for equalization, use statistical simulations to kind of get a different feel for how the interface performance is and what the equalization looks like. This last slide shows again our simulation strategy for power integrity. What I'm showing on the left is the measured power noise, and on the x-axis is the low-pass filter bandwidth. So we can look at the frequency spectrum of the measured power noise, and if you look closely, about 90% of the noise is within 10 megahertz, and only a small component of the noise is at a much higher frequency. Now, based on this information, you can devise your simulation strategy wherein you use the right tools to do do the package PCB and interposer extraction, and then you use the right tools to do the on-die power integrity. And there are options to do co-simulation. I'm sure the other speakers are going to talk about co-simulation as well. So that's the key takeaway from this slide. In summary, most products have tight design cycles and time to market, and each project goes through different phases. So at each phase, it is good to have a goal-oriented simulation strategy so that your design can move across those stages, and you can be smart about the right simulations tools to go with each phase so that you are able to get design closure and you are able to get design success. Thank you.